Are you fascinated by the internet and the vast amount of information it provides at your fingertips? Well, have you ever wondered how it all works? How you can access websites from across the globe, stream movies, and communicate with people all over the world in real time? The answer is computer networking. In this video, we'll take you on a journey from fundamentals of computer networks to a more advanced concepts which every cybersecurity individual should be aware of. So, what is a computer network? Simply put, it is a collection of interconnected devices that can communicate with each other. These devices can be computers, printers, servers, routers, switches, and other hardware components. At the heart of any computer network is the idea of communication. Devices in a network can share information resources with each other, and this is done using a set of rules and protocols. One of the key components of a computer network is the transmission medium, which is the physical pathway that carries information between devices. This can be a wired medium such as Ethernet cables or a wireless medium such as Wi-Fi. Then how data is transmitted over a network? So the data is broken down into smaller pieces called packets, which are then sent over the network to the destination. Each packet contains information such as the source and destination addresses as well as the actual data being transmitted. The communication between these devices is made possible through a set of rules and protocols known as this network's protocol stack. This stack is made up of several layers, which is called as network model, of which the most common one is the OSI model. The OSI model is a conceptual framework that helps us understand how data flows through a network. So let's break down these 7 layers of the OSI model and explain what each layer does. The Open Systems Interconnection Model, also known as OSI model, is a crucial component of computer networking, and understanding it is essential for any aspiring network engineer or IT professional. The OSI model is divided into 7 layers, each with its own unique function in the communication process. These 7 layers are physical, data link, network, transport, session, presentation, and application. Let's take a closer look at each of these layers. Firstly, physical layer. This is like the postal service that delivers mail to your mailbox. Just like the postal service handles the physical delivery of mail, the physical layer handles the physical transmission of data over the network. This layer deals with things like cables, connector, and other hardware. Next is the data link layer, which is like the person who puts the letter in an envelope and seals it. This layer is responsible for framing data packets, adding error detection and correction codes, and controlling access to the network media. Nextly, the network layer. Network layer is like a GPS that helps navigate the mail delivery truck to the right location. This layer is responsible for routing data packets between different networks, and it uses logical addressing and routing protocol to do so. Nextly, we have transport layer. The transport layer is like a courier who ensures that the letter is delivered to the right recipient. This layer is responsible for reliable delivery of data packets, flow control, and error recovery. It uses protocols like TCP and UDP to provide these services, which we'll look into in detail later. The next layer is the session layer. It is like the person who arranges a meeting between two parties. This layer establishes and manages sessions between applications running on different devices, allowing them to exchange data. Next is presentation layer. The presentation layer is like a translator who translates a letter written in one language into another language. This layer deals with data formatting, encryption, and compression. Finally, the application layer. The application layer is like the person who writes the letter and sends it. This layer provides services to application programs such as email, file transfer, and web browsing. So, to summarize, the OSI model is a crucial component of networking. It defines how data is transmitted and received over network and provides a framework for network engineers and IT professionals to design, implement, and troubleshoot networks. Understanding the OSI model is essential for anyone who wants to work in the field of computer networking. So let's break down the important layers and explore the individual roles. Physical network. While talking about physical network, there are two important concepts which we need to look into. First is cabling and topologies, and the next one is Ethernet. So let's first look into the cabling and topologies. Cabling and connectors are an essential part of any network infrastructure. When it comes to building a network, you need to choose the right type of cable and connector that suits your need. There are various types of cables such as coaxial, twisted pair, and fiber optic, and each has its own advantages and disadvantages. For instance, twisted pair cable is the most commonly used type of cable for Ethernet networks. It consists of 4 pairs of wires that are twisted together to reduce interference and crosstalk. On the other hand, fiber optic cables use light to transmit data over long distances and are preferred for high-speed networks. Connectors, on the other hand, are used to connect cables to network devices such as switches, routers, and computers. Some of the most common connectors include RJ45, BNC, and ST. For example, RJ45 connectors are used to connect Ethernet cables to the network devices, while BNC connectors are used in coaxial cables for cable TV connections. In addition to choosing the right type of cable and connector, network topologies also plays a crucial role in determining the efficiency and reliability of a network. A network topology refers to the physical or logical arrangement of network devices and their interconnections. Some common network topologies include star, bus, and ring topologies. For instance, a star topology connects all devices to a central hub or switch, which can reduce the impact of a single device failure on the entire network. In contrast, a bus topology connects all the devices to a single cable, which can lead to a single point of failure. Choosing the right cabling and connectors and selecting an appropriate network topology are crucial steps in building a robust and reliable network. It is important to understand the pros and cons of each option before making a decision, as this can have a significant impact on the performance and stability of your network. Next is Ethernet. Ethernet is a fundamental concept in computer networking, and understanding its basics is crucial for any networking professional. At its core, Ethernet is a set of protocols that define how data is transmitted over a network. One of the most important aspects of Ethernet is its use of carrier-sense multiple access with collision detection, which helps to prevent multiple devices from transmitting at the same time, which could result in data collisions and the loss of information. Another key element of Ethernet is the use of frames to transmit data, which consist of source and destination addresses, data payload, and error detection information. Ethernet frames are transmitted between devices using a variety of cabling and connector types, such as twisted pair cables, fiber optics, and RJ45 connector, which we explained above. So we've got connection. What if we want to extend the network? So for this, two key components in Ethernet networks are used, which are hubs and switches. Hubs are simple devices that receive data from one port and broadcast it to all other ports, while switches are more intelligent devices that can direct data to specific ports based on the destination MAC address. Hubs were commonly used in the past but have largely been replaced by switches due to their efficiency and potential for network congestion. Switches allow for more efficient and secure communication between devices on the network, as they can isolate traffic to specific ports and prevent unnecessary broadcasts. For example, in a home network, a switch can ensure that data from a gaming console goes directly to the internet without being broadcast to all other devices on the network. This can improve network performance and reduce the risk of security breaches. Ethernet has evolved over the years with faster speeds and new technologies such as Power over Ethernet and virtual LANs, enabling more efficient and effective networking. With the rise of Internet of Things and increasing demand for high speed and reliable network connectivity, Ethernet remains an essential component of modern computer networking. TCP/IP. While discussing about network models, I mentioned only OSI model, but that's not the only model available. TCP/IP model, which is often preferred by IT professionals because it is simpler and more flexible than the OSI model. It is also the protocol suite that is most commonly used in the internet and many other networks. The application layer in the TCP/IP model corresponds to the top three layers, which is application, presentation, and session of the OSI model, while the transport layer in the TCP/IP model corresponds to the OSI transport layer. The internet layer in this model corresponds to the OSI network layer, and the network access layer in this model corresponds to the bottom two layers, which are data link and physical layer of OSI model. Before diving into the working of this TCP/IP model, let's look into the protocols used in each of these layers. Firstly, the link layer counts on technologies outside the TCP/IP protocol suite like Ethernet, cable modem, or DSL to get the IP packets from one system to the next. So technically it's not part of the IP protocol suite. So let's look into other layers protocols. Internet layer protocols. Internet protocol is a network layer protocol responsible for routing data packets between devices in a network. There are two versions of IP, IPv4 and IPv6. IP version 4 is the older version of IP and is still widely used today. It uses 32-bit address space, which allows for approximately 4 billion unique addresses. IPv4 addresses are typically represented in dotted decimal notation with 4 numbers between 0 to 25 separated by dots, such as this one. So IPv4 addresses are divided into two parts, one the network portion and the host portion. The network portion identifies the specific network while the host portion identifies the specific device on that network. IPv6 is the newer version of IP and was developed to address the exhaustion of IPv4 addresses. It uses a 128-bit address space, which allows for approximately 3.4 into 10 to the power of 38 unique addresses. IPv6 addresses are typically represented in hexadecimal notation with 8 groups of 4 hexadecimal digits separated by colons, such as this one over here. IPv6 addresses are divided into 3 parts: the routing prefix, the subnet, and the interface ID. The routing prefix identifies the specific network, while the subnet ID identifies a specific subnet within that network, and the interface ID identifies a specific device on that subnet. Both IPv4 and IPv5 are still used in today, but IPv6 is slowly gaining popularity as more and more devices connect to the internet and require unique addresses. Understanding the difference between these two versions of IP is important for IT professionals who manage and maintain networks, as well as for developers who build applications that rely on network connection. And the next protocol is ICMP, which is Internet Control Message Protocol, This protocol is used by network devices to report errors and provide feedback to other devices. For example, if a packet is lost or cannot be delivered, ICMP will generate an error message that is sent back to the source device. Address Resolution Protocol, also known as ARP, this protocol is used to map IP addresses to MAC address. When a device wants to send a packet to another device on the same network, it first needs to know the MAC address of that device. ARP is used to resolve this mapping. And the next one is the Reverse Address Resolution Protocol, which is RARP. This protocol is used to map MAC addresses to IP addresses. It is used in situations where a device does not have a pre-configured IP address and it needs to obtain one dynamically. Now let's look into the transport layer protocols. Transport layer protocols are responsible for reliable and efficient transmission of data between end-to-end hosts over a network. There are two primary transport layer protocols. One is Transmission Control Protocol (TCP) and another one is User Datagram Protocol (UDP). TCP is a reliable connection-oriented transport layer protocol that provides error checking and flow control mechanism to ensure data is transmitted reliably between two hosts on a network. When establishing a TCP connection, a three-way handshake is used between the client and the server to ensure the connection is valid before data transfer begins. The three-way handshake begins with the client sending a synchronized packet to the server to initiate the connection. The server responds with a synchronized acknowledged packet to acknowledge the client's request and establish the connection. Finally, this client sends an acknowledged packet to confirm that the connection has been established and the data transfer begins. The TCP header contains information such as the source and destination port numbers, sequence and acknowledgement numbers, and the control flags. The sequence number is used to keep track of the order of the data being transmitted, while the acknowledgement number is used to acknowledge receipt of data. The control flags include options such as sync acknowledge, fin which is finish, and RST which is reset flags, used to establish, maintain, and terminate the connection. In addition to the three-way handshake and header information, as we said, TCP provides flow control and congestion control mechanisms. Flow control helps prevent the receiver from being overwhelmed with too much data at once, while the congestion control helps prevent network congestion by reducing the amount of data transmitted when the network becomes congested. UDP, User Datagram Protocol, is a transport layer protocol that is used for sending datagrams over an IP network. Unlike TCP, UDP does not establish a connection before sending data and does not provide reliable delivery or congestion control. Instead, UDP is designed for applications where speed and low overhead are more important than reliability. UDP datagrams consist of a header and a payload. The header includes the source and destination port numbers, length of datagram, and a checksum for error detection. The payload contains the actual data being sent. Unlike TCP, UDP does not have a handshake process to establish connection between the sender and the receiver. Instead, the sender simply sends the datagram to the receiver's IP address and port number. If the receiver is not listening on that port, the datagrams will be discarded. Since UDP does not provide reliability or congestion control, it is often used for real-time applications such as online gaming, voice over IP, and streaming videos. In these applications, a few lost packets are usually acceptable as long as the overall experience remains smooth and uninterrupted. Now let's look into the application layer protocol. It is the topmost layer in the TCP/IP protocol suite and is responsible for supporting network applications and providing network services to the end user. It interacts with the software applications running on the system and provides a platform for those applications to access the network. The application layer protocols are a set of protocols that enable connection between applications over a network. These protocols include HTTP, SMTP, FTP, Telnet, SSH, DNS, and many more. Let me give you a short description about these protocols. Firstly, HTTP, Hypertext Transfer Protocol, is a protocol used for accessing the World Wide Web. It is used to retrieve web pages and other resources from servers on the internet. SMTP, Simple Mail Transfer Protocol, is the protocol used for sending email messages between servers on the net. It is responsible for routing and delivering email messages to the correct destination. FTP, File Transfer Protocol, is the protocol used for transferring files between computers on a network. It allows users to upload and download files to and from remote servers. Telnet is a protocol that allows remote access to a computer over a network. It provides a virtual terminal that allows users to execute commands on a remote system as if they were sitting in front of it. SSH, Secure Shell, is a protocol that provides secure remote access to a computer over a network. It encrypts all data transmitted between the client and the server, making it more secure than Telnet. DNS, also known as Domain Name System, is the protocol used to translate domain names into IP addresses. It provides a way for users to access resources on the internet using domain names rather than the IP address. These protocols are essential in enabling communication between different applications running on a network. They provide a common language that allows the applications to communicate and exchange data regardless of the platform or programming language used to develop them. Now that we have looked into all the protocols, let's look into the IP address in action. Firstly, we'll look into the IP address working within the LAN network. Let's say you have two computers, one is host A and host B, connected to the same Ethernet LAN. Host A wants to send a message to host B. First, host A needs to determine the IP address of host B. It sends an ARP request to the LAN asking for the MAC address of host B associated with its IP address. The ARP request is broadcast to all devices on the LAN, including host B. When host B receives the ARP request, it responds with its MAC address. Now that host A has the MAC address of host B and can send the message, it creates an Ethernet frame with the MAC address of both computers and the message payload. The frame is then sent over the Ethernet LAN to the destination MAC address. Host B receives the Ethernet frame and checks if the destination MAC address matches its own MAC address. If it does, it extracts the message payload and delivers it to the appropriate application on the computer. This is just a basic example, but it illustrates how IP addresses and Ethernet work together to enable communication between devices on a network. Now let's look into the working of IP across networks. Before looking into the actual working, let's look into a few concepts. Firstly, the concept of network ID, subnet, and class ID, which are really useful to help organize and identify devices on a network. The network ID is a unique identifier that is assigned to a network. It is used to distinguish one network from another, and it helps routers determine where to send data packets. For example, if a computer wants to send a message to another computer on the same network, it sends the message directly to that computer using the network ID. Subnetting is a technique used to break down a large network into smaller subnetworks or subnets. This helps to improve network efficiency, manageability, and security. Subnetting involves dividing the IP address space of a network into smaller, more manageable subnet, which can be assigned to different parts of the network. For example, consider a network with the IP address range of 192.168.0.0/24. This means that there are 256 IP addresses available in the network, ranging from 192.168.0.1 to 192.168.0.254. However, if the network needs to be divided into smaller subnetting can be used. Let's say we want to divide the network into 4 subnets. This would require us to borrow 2 bits from the host portion of the IP address. The subnet mask for this would be 255.255.255.192, which means that each subnet would have 64 IP addresses available. Using this subnet mask, the 4 subnets would have the following IP address range. So each subnet has its own network ID and broadcast address, which are the first and last address in the subnet respectively. For example, the network ID for subnet 1 would be 192.168.0.0 and the broadcast address would be 192.168.0.63. Subnetting allows for more efficient use of IP addresses and can help to reduce network congestion and improve network performance. It also allows for more granular network segmentation, which can enhance network security and simplify network management. There is another technique similar to subnetting, which is CIDR, classless interdomain routing. CIDR uses a notation that combines the IP addresses and the subnet mask in the following form of slash followed by the number of bits in the subnet mask. For example, 192.168.1.0/24. So here the 24 is the number of ones in the binary form of this IP address. This represents a network address of 192.168.1.0 with a subnet mask of 255.255.255.0. The class ID refers to the type of network address that is being used. It is based on the first few bits of an IP address and is used to identify the network and host portions of the address. There are 5 classes of IP addresses. The classes A, B, and C are commonly used for addressing devices on a network, while classes D and E are reserved for special purposes. For example, if a network has the IP address range of 192.168.0.0/24, the network ID will be 198.168.0.0 and the subnet mask would be this. This would allow for up to 254 devices to be assigned IP addresses on a network, and any devices on the subnet could communicate with each other directly. The class ID for this IP address range would be class C. Now let's look into the working of IP across networks. Suppose we have a LAN with 2 subnets, subnet A and subnet B, connected by router. Computer 1 is on a subnet A with IP address 192.168.10 and the computer 2 is on the subnet with the IP address 192.168.2.20. If computer 1 wants to send a message to computer 2, it needs to know the IP address of computer 2. So it will first check its own subnet and see that computer 2's IP address is not on its own subnet, so it needs to send the message to the router. Computer 1 will then use its default gateway address, which is the IP address of the router, to send the message. The router will receive the message and check its routing table to see that the destination address is on the subnet B. The router then forwards the message to the computer 2's IP address on the subnet B. If computer 1 wants to send a message to another computer on subnet A, say computer 3 with IP address 192.168.1.115, it does not need to send a message to the router. It will simply send the message directly to computer 3's IP address since it's on the same network as computer 1. So in summary, when sending a message across a LAN with multiple subnets, a computer will first check if the destination IP is on its own subnet. If not, it will send a message to the router's IP, which is the default gateway, which will forward the message to the appropriate subnet. While we are in the topic of IP address, let's look into the IP address assignment. Imagine you are setting up a small network for your office. You have 5 computers that need to be connected to the network. Each computer needs to have its own unique address to be able to communicate with each other devices on the network. To assign IP addresses, you can use a system called DHCP, Dynamic Host Configuration Protocol, which automatically assigns IP addresses to devices as they join the network. Alternatively, you can use a static IP address where you manually assign a specific IP address to each devices. Let's take a closer look at DHCP. When a device joins the network, it sends a request for an IP address to the DHCP server. The DHCP server then assigns a unique address to the device, along with other network configuration information such as the subnet mask and default gateway. This process ensures that each device on the network has a unique IP address and that they are configured to communicate with each other. Now let's consider the static IP addressing. In this case, you manually assign a specific address to each device on the network. This method is useful in situations where you need to control the IP addresses that are assigned to each device, or when you have devices that require a static IP address for specific applications. It is important to understand the difference between these two methods and to choose the method that is appropriate for your specific needs. Routers. Although I've touched upon routers before, now we'll look in detail about its functions and what are they used for. Routers are networking devices that allow communication between different networks, such as connecting a local network to the internet. They work by forwarding data packets based on the destination IP address. So the main job of router is to read the information like the source IP and destination IP address and determine the best path to forward the packet to its destination. So while talking about routers, we need to look into a concept called routing table. Routers maintain a routing table that lists the available routes to each different networks. The routing table contains information about the IP addresses of all connected devices and networks, as well as the routers to reach them. The router uses this information to determine the best path to forward a packet based on its destination IP address. A routing table is typically a list of entities that include the following information. So the first is destination network, which is the IP address of the network that the packet is trying to reach. Then the subnet mask. The subnet mask specifies which portion of the IP address is used to identify the network and which portion identifies the host. Next hop. The IP address of the next router or interface to which the packet should be sent to reach the destination network. Interface. The network interface on the local router through which the packet should be sent. Metric value. So it's a value that indicates the cost of sending data packets to the destination network through the specified next hop. The routing table is populated in one of the two ways. One is dynamically and another one is statically. Dynamic routing protocols such as OSPF, BGP and RIP can be used to automatically update routing tables based on the changes in the network topology. Statically configured routers can also be added to the routing table manually. When a router receives a packet, it examines the destination IP address to determine the best path for the packet to reach its destination. It does this by consulting its routing table. The router looks for a routing table entry that matches the destination IP of the packet. If there is a match, the router forwards the packet to the next hop specified in the routing table entry. If there is no match, the router uses the default route to forward the packet. The routing table includes a metric value for each routing table entry. This metric value is used to determine the best path for a packet to reach its destination. The lower the metric, the more preferred the route. If there are multiple routes with the same metric, the router may use the other criteria such as bandwidth, delay, and reliability to choose the best path. As I told you before, routing tables are not static. They are constantly updated as change occurs in the network topology. When a router receives an update from a dynamic routing protocol, it updates its routing table accordingly. And the router may also periodically send out routing table updates to neighboring routers to inform them of changes in the network topology. The next concept we're gonna look is network address translation. It is a technology used by routers to translate between IP addresses used on a private network and the IP addresses used on the public network. NAT allows multiple devices on a private network to share a single public IP address, which can help conserve IP address space. So the NAT works by translating between private IP addresses and public IP addresses. Private IP addresses are used on the internal network and are not routable on the internet. Public IP addresses are assigned by ISP, which is the Internet Service Providers, and are used to identify devices on public internet. When a device on a private network sends a packet to a device on a public internet, the NAT router replaces the source IP of the packet with its own public IP address. When the response packet comes back from the public internet, the NAT router translates the destination IP address back to the private IP address of the original device and forwards the packet to the appropriate device on the internal network. There are several types of NAT, and let's look few of those. So the first is static NAT. This type of NAT maps a single private IP address to a single public IP address. Static NAT is useful for servers that need to be accessed from the internet. Dynamic NAT. This type of NAT maps a pool of private IP addresses to a pool of public IP addresses. Dynamic NAT is useful for networks within a large number of devices that need to access the internet. Next is port address translation. This type of network NAT maps a single public IP addresses to multiple private addresses using different port numbers. PAT is commonly used by home routers to allow multiple devices to share a single public IP address. NAT provides a level of security by hiding the internal network from the public internet. Since private IP addresses are not routable on the internet, devices on the internal network are not directly accessible from the internet. This can help protect against unauthorized access and attacks from the internet. While NAT can provide a number of benefits, there are some limitations to consider. For example, NAT can cause issues with certain type of application that require direct access to devices on the internet. NAT can also make it more difficult to track and manage network traffic. The next concept is DNS. The DNS, known as Domain Name System, is a distributed system that translates human-readable domain names such as www.example.com into IP addresses that are used to identify and communicate with web servers and other network resources. So the DNS system is organized into a hierarchical structure of domains, with each domain consisting of a label separated by dots. For example, this domain name is composed of labels www, example, and .com. When a user types a domain name into the web browser or other network application, the application sends a request to the DNS resolver, typically provided by the ISP. The resolver then begins the process of resolving the domain name into an IP address. The resolver starts by querying a set of root DNS servers which are maintained by the Internet Assigned Numbers Authority. These servers are responsible for directing the resolver to the appropriate top-level domain servers based on the domain name being resolved. The resolver then queries the TLD server associated with the domain name being resolved. In this case, the .com TLD server, which responds with the IP address of the authoritative DNS server responsible for the next level of domain name hierarchy. The resolver then queries the authoritative DNS server for the next level of domain name hierarchy. In this case, the DNS server responsible for the example.com domain, which responds with the IP address of the web server associated with the requested domain name. Finally, the resolver caches the IP addresses it received from the authoritative DNS server so that the subsequent requests for the same domain name can be resolved more quickly without requiring a full DNS lookup. Now that we have learned all about the fundamentals of computer networking, let's look into the more advanced concepts. These are the topics that will take your networking skills to the next level. The first one is Virtual Private Network, also known as VPN. It is a technology that allows remote users to securely connect to a private network over the internet. It enables users to securely access and transmit data over the public network as if they were directly connected to a private network. The primary function of a VPN is to establish a secure and encrypted connection between a user and a network, typically over the internet. The VPN also has VPN protocols, which are a set of rules and procedures used to establish a secure connection between the user and VPN server. The most common VPN protocols are PPTP, which is point-to-point tunneling protocol. This protocol is an older VPN protocol that is widely supported on various operating systems. It uses a 128-bit encryption key to secure the data traffic, which is not as strong as the other protocols. However, it has a faster connection speed and lower overhead than other protocols, making it a good choice for streaming media and online gaming. The next is Layer 2 tunneling protocol with Internet Protocol Security. It is a combination of two protocols that provide strong encryption and authentication. It is a widely used protocol and is supported by most devices. It uses a 256-bit encryption key, which is stronger than PPTP, but it can be slower due to the overhead of encryption. The next one is OpenVPN. It is an open source VPN protocol that uses SSL/TLS for encryption and authentication. It is highly configurable and can be used on various platforms including Windows, Linux and Mac OS. OpenVPN uses a 256-bit encryption key and offers a high level of security. And the next one is the Secure Socket Tunneling Protocol. SSTP is a Microsoft developed VPN protocol that uses SSL/TLS for encryption and authentication. It is supported on Windows and Linux system and offers strong security with a 2048-bit encryption key. SSTP is a good choice for those who need to bypass firewalls or other network restrictions. When a user connects to a VPN, the traffic is encrypted and sent to the VPN server. The server decrypts the traffic and sends it on to the destination. The destination sees the traffic as coming from the VPN server, not the user's device. This ensures that the user's IP address and location remain hidden. Let's say, for example, imagine a user is working remotely from a home and needs to access the company's network. They connect to a company's VPN using their device and login credentials. Once connected, they can access the company's network as if they were physically present in the office. The VPN encrypts that traffic and ensures that sensitive information is not intercepted by unauthorized users. Then the next topic is virtualization. Virtualization is the process of creating a virtual version of something, such as operating system, server, storage device, or network resources. In computing, virtualization involves using software to create a virtual environment that can emulate hardware and software from a physical environment, allowing multiple virtual instances to run on a single physical host. There are different types of virtualization such as server, desktop, storage, and network. Each type has its own purpose and benefits. For example, server virtualization allows multiple virtual servers to run on a single physical server, which reduces hardware cost and increases resource utilization. Desktop virtualization allows multiple virtual desktops to run on a single physical desktop. It simplifies desktop management and provides secure remote access. Storage virtualization allows multiple storage devices to be managed as a single virtual storage pool, which simplifies storage management and improves data availability. Network virtualization allows multiple virtual networks to run on a single physical network infrastructure, which provides flexibility and reduced costs. Virtualization is made possible by a software layer called hypervisor, which creates and manages the virtual environment. The hypervisor sits between the virtual machines and the physical hardware and manages access to the underlying resources, such as CPU, memory, and storage. There are two types of hypervisor. Type 1 hypervisor, also known as native or bare metal hypervisors, run directly on the host hardware and provide direct access to hardware resources. Type 2 hypervisor, also known as hosted hypervisor, run on top of the operating system and rely on the host's hardware resources. Overall, virtualization provides numerous benefits including cost saving, resource utilization, scalability, flexibility, and disaster recovery. It has become an essential technology for many organizations, especially those with large IT infrastructures. Finally, cloud networking. Cloud networking refers to the use of cloud computing infrastructure and resources to build and manage computer networks. Instead of relying on on-premise hardware and software, cloud networking allows business to use virtualized resources to build, scale, and manage their network more efficiently. One example of cloud networking is AWS, Amazon Web Services. AWS provides a variety of networking services such as virtual private cloud, which allows users to create isolated virtual networks within the AWS cloud. This VPC can be customized with specific IP addresses, subnet, and routing table, and can be connected to other networks using VPN or direct connect services. Another example is Microsoft Azure, which provides networking services such as VirtualNet and ExpressRoute. VNets allow users to create virtual networks in the cloud and can be configured with various network security features like firewall and network security groups. ExpressRoute provides a dedicated private connection between on-premise data center and Azure VNet, enabling users to create a hybrid cloud environment. Cloud services can be categorized into three main types: infrastructure as a service, platform as a service, and software as a service. Infrastructure as a service provides the basic infrastructure for computing, such as virtual servers, storage, and networking that can be used to build and manage applications. PaaS provides a platform for developers to build, test, and deploy applications without the need to worry about infrastructure. SaaS provides ready-to-use software applications that are hosted and managed by the CSP, such as email, collaboration tools, or customer relationship management CRM systems. One example of cloud service is AWS, which is a infrastructure as a service offering from Amazon. With AWS, users can create virtual servers, store data, and use other infrastructure services without having to purchase and maintain physical hardware. Another example is Microsoft 365, which is a SaaS, software as a service, offering that includes email, file storage, and productivity applications like Word, Excel, and PowerPoint. Cloud networking also includes the use of software-defined networking technologies, which allow for greater network agility and flexibility. SDN enables users to centralize network management, automate network configuration and deployment, and dynamically allocate network resources based on application demand. Cloud services provide many benefits, including cost saving, scalability, flexibility, and ease of use. They also allow organizations to focus on their core business instead of managing infrastructure, and provide access to powerful computing resources that may not be available in-house. That's it for this video. Thank you for watching till the end of this video, and I hope this video has given you solid foundation and understanding of fundamental concepts that are essential to building and maintaining modern computer networks. Whether you are interested in pursuing a career in networking or simply want to improve your knowledge for personal and professional growth, remember that learning is a continuous process. So keep exploring, keep experimenting, and keep building. The world of computer networks is constantly evolving, and there is always something new to discover. So thank you for watching this video, and I wish you all the best in your networking endeavors.